Now is the time for us to discuss an important kind of graph or diagram called the PV diagram. I'm here to spread the good word of the PV diagram. PV means pressure volume, so it's exactly what you might expect. You plot pressure on the vertical axis and volume on the horizontal axis. Okay? It turns out most interesting thermodynamic processes can be plotted inside of this kind of diagram, and you can learn a lot about it. The reason you can learn so much about it, if you think back to the last video, is that pressure and volume tell you about how much work is done. Okay, so if I have some process going through the PV diagram, okay, the work done is actually just the area underneath this curve. Okay, pressure times volume added up, all the little bits of it, as I said, and that will tell you how much work is done. Well, okay. So what else about them? I mean, I could draw out a lot of different processes this way. For example, we could have some process that goes maybe some kind of expansion, pressure drops as you go, maybe some kind of contraction, pressure drops, and something back up. Okay? The area inside of here is the amount of work done by that process. Okay? You'll notice, by the way, that when I go this direction, clockwise, the work is positive, although it turns out if I go the other way, counterclockwise, I get negative work. Okay? Negative work in this case means I have to do work to make the system go in that direction. I might get something out of it I like, but I'm going to have to apply work from outside. So to be a little more specific about some interesting things that happen on PV diagrams, there's 4 special curves that we can talk about. Okay? One is called an isocore. Sorry, let's start with the isobar rather. Isobars happen at constant pressure. Okay? You've encountered isobars, you may have even heard the name. If you ever look at certain kinds of weather graphs, you'll see isobars, areas of constant pressure on the graph. Okay? Bar is in barometric pressure. Isobar, got it. Okay? Isobars are nice because the work done by one of these, by the way, is really just P delta V. Because the pressure is constant, we don't have to do any kind of calculus fanciness. Well, okay, we can hold the pressure constant, or we could hold the volume constant. Okay? Constant volume is just a vertical line on this. Turns out the term for that is isocore. Don't ask me why, I don't really know. Okay? That's the second thing. The amount of work done by an isocore is always 0, by the way, because the change in volume is 0. Now there's 2 more special kinds of curves on here we can talk about. The first is an isotherm, constant temperature. Well, if you think about the ideal gas law, PV equal nRT, I'm going to write the chemistry version. We know then that the relationship between pressure and volume is PV equal nRT over V. So there's some constant here over V, so that's a hyperbola coming down. So this is an isotherm. Okay? The final kind of curve we can get, this is a very specific, by the way, swoop down. The final kind of curve we can get is called an adiabat. Also sometimes called an isentrope, but we'll get into that later. An adiabat is what you get when no heat is allowed to enter or leave the gas in question, the chamber in question. I'm not going to go into why this curve looks like this, but what you get is another swoopy down curve that's got a steeper slope. In general, it depends exactly, the slope depends exactly which gas is in there, it turns out. But this is an adiabat. These come up a lot because any process where heat either doesn't have time to move, so if you do something very, very quickly, or you have a lot of insulation wrapped around things, you get an adiabat. Or the other option is sometimes if you don't want the temperature change too much because you do it slowly, it's also going to be adiabatic. Okay? These curves are going to turn out to be the sort of cornerstone set of curves for most of the processes we're going to theoretically consider as possible engines. Now, real engines, it turns out, don't actually follow these digital curves. There's no such thing as a perfect isotherm. There's no such thing as a perfect adiabat. Okay, and in general, because you make a lot of sacrifices when you put together an engine, you give up a lot of sort of the perfect ideal engine model. Okay, I want this to be as close to adiabatic as possible, but then you go, well, that's going to cost a lot of money. I'm going to need a lot of very fancy high-end materials for that, and the customers don't want to pay $1 million for a car. So then you start making sacrifices and you get not perfect things. But when we're thinking theoretically about them, we're going to be thinking about these curves. So get to know the isocore, the isobar, the isotherm, and the adiabat really, really well. All right, see you on Friday.